Section 4.3, Logarithmic Functions, Part 3. In this part of the video, we'll be focusing on properties of logarithms. In this section, we're going to focus on properties of logs that enable us to expand or condense expressions using logs. The first property that we're going to look at is the product property. So if we have log base a of x times y, so we're multiplying two things like x and y, we can rewrite that using addition. So log base a of x plus log base a of y. So multiplication and addition are ways. Next, we have the quotient property. Remember, quotient means to divide. So if we have log base a of x divided by y, we can rewrite that using subtraction. So we get log base a of x, or whatever was on the top, minus log base a of y, or whatever was on the bottom. Our third and final property is the power property. So remember, power means exponent. So if we have log base a of x to the r, so r is an exponent on the x, we can move the r out front and make it r log base a of x. So I like to say that exponents fly out front. So it goes out front. A couple other properties that you may want to make note of. Log base a of 1 is always equal to 0. So if the argument is a 1, we're going to have it equal to 0. Also, if we have log base a of a, we just get out our answer of 1. Example 5, part A. We're going to rewrite this expression using multiple logs. So first of all, we're going to always, and I like to call this expanding, by the way. So I'm going to expand it so that my answer has multiple logs, and each log has one base in it. So in the argument here, I see an x, a y, and a z. So I know that those are going to be in each of the logs at the end. So I'll have 3 logs. We're going to start by looking at division here. So since I have division going on, I can rewrite this as log base 6 of the top minus log base 6 of the bottom. I always like to put the arguments for each log in parentheses. Next, we're going to focus in on the multiplication that's going on right here between our x and our y. So we have log base 6 of x squared plus log base 6 of the cube root of y. And we still have minus log base 6 of z. The last thing I'm going to do is look at my exponents. So I have x squared. That 2 is going to fly out front of the log. Don't forget that cube root of y is just y to the 1/3. So then I'll have a 1/3 move out front for that one. And log base 6 of z is already simplified as far as it can go. One more thing to note, the problem started with a base 6. So notice every time I wrote a log, I put base 6. If I were to not put base 6, then this would be wrong. The 6 doesn't do anything in the problem, but we need to carry it along each time we write log. Example 5, part B. We're going to do the same thing here, but this time we're going to start with the square root since it is all over everything in the argument. So I'm going to rewrite the square root as to the 1/2 exponent. And then I'm going to distribute that 1/2 into each of my exponents by multiplication, because this is like the power to a power rule. So x to the 4th to the 1/2 is going to be x squared. 4 times 1/2 is 2. Y to the 1/2 is just going to be y to the 1/2. And z to the 3rd to the 1/2 is going to become z to the 3/2. Next, we're going to focus on division. So I'm going to take log base 2 of the top minus log base 2 of the bottom. Next, we're going to look at the multiplication going on between the y and the z. Something I want to point out really quick is the fact that we have a subtraction sign in front of that second log. So we're going to put this in brackets, and eventually we're going to have to distribute that negative into both logs. So watch for my orange brackets in the next step. So log base 2 of x squared stays the same, minus, and now I'm going to break that log up into 2 logs with an addition symbol. Okay, so now what I'm going to do is I'm going to take the negative that's in front of the orange brackets and I'm going to distribute it. And then the last thing I'm going to do is my exponents. They're going to fly out front of each of the logs. So the 2 is going to go out front of the first log, the second log will have a 1/2, and the third log will have the 3/2. Remember, since the problem started with log base 2, every log that we write down needs to have a base 2 on it. Example 6. In this example, we are going to write this expression as a single logarithm. So we're going to condense it into one log. The first thing that we're going to look for is what would be exponents. So I'm looking in front of each of the log terms to see if there's a coefficient out front. And we have 1/3 and 5, which are going to become exponents. Remember, f to the 1/3 is just the cube root of f. Okay, so now we're going to look at using the subtraction that's going on between the 3 logs. So this first term, since it comes first, is going to go on top. Remember, subtraction means division, so we're going to have a fraction going on here. And then both of these terms that are being subtracted off are going to go on the bottom. So cube root of f on the bottom and r to the 5th on the bottom. So now we can write our final answer. Still have log base d. M is on the top of the fraction, and both f and r are in the denominator. And that's your final answer. Example 6, part B, same idea. First thing I want to point out, though, is that we have log of x plus 3. So keep in mind, if there's a sum or a difference inside the log, then it's always going to stay like that. Don't think about breaking up the x and the plus 3. Just leave them like they are. So let's start by looking for exponents. The only number that would be an exponent here is 6. So that's going to come up and be an exponent on our x. Next, we're going to look at the addition and the subtraction going on. So addition between the first 2 terms means that we're going to multiply the x plus 3 and the x to the 6th. So those are both going to go on top, because then we're going to divide by 2. That's what the minus log of 2 means. So the first 2 will be in our numerator. They're going to go on top of the fraction. And the last one, since it's being subtracted off, will be in the denominator. So here's our final answer. I don't think My Math Lab will make you distribute the x plus 6, but if you did, you would have x to the 7th plus 3x to the 6th. So I think it's fine how it is, and that's your final answer. Example 7, we're going to use values that we know for logs to simplify or evaluate other logs. So for example, in this problem, we know that log base 10 of 2 is equal to the decimal 0.3010. So we're going to evaluate log base 10 of 4 using that fact. So the first thing I want to do is I want to take that 4 and rewrite it using 2. So instead of 4, we're going to use 2 squared so that it's base 2. Next, we can use one of our properties where we take our exponent and we put it out front. And then we have 2 times log base 10 of 2. Well, we know what log base 10 of 2 equals. Looking back up at the problem, that's just 0.3010. So let's plug that in and then use our calculator here, and we get a final answer of 0.602. Example 7, part B. Same idea this time. We've got log base 10 of 5. So I need to rewrite that 5 somehow using a 2. I'm not going to be able to do it as 2 to a power. So this time I'm going to write it as 10 divided by 2, and you'll see why here in a minute. So rewrite 5 as 10 divided by 2. We can use our quotient rule here since we have division going on inside of the log. So we'll have log base 10 of the top minus log base 10 of the bottom. Now, anytime we have log base 10 of 10 or log base 2 of 2 or log base 7 of 7, anytime those two are the same numbers, it's actually just going to be equal to 1. So this first term, we just get 1. And then the second term, log base 10 of 2, we know is 0.3010. So our final answer is 0.699. We talked about this a little bit in that last example there, but here it is defined for you whenever we're talking about inverses here. So if we have base A with an exponent of log base A of x, then the base A and the log base A cancel out, and our answer is just whatever is in this x spot. Likewise, if we have log base A of A to the x, then again it's just x. On that last problem, I had log base 10 of 10. Technically, it was to the 1 power, and that's why that one was equal to 1. Here's a few examples that involve this theorem. So the first one, if I have base 7 and then my exponent is log base 7 of something, then that's just my answer right there. So the base 7 and the log base 7 would cancel out. Same thing here with log base 5 and a base 5. They both cancel out, and my answer is just the exponent, which is 3 in this case. And again, log base r of r, those are going to cancel out, and your answer is just the exponent. Why don't you go ahead and add this one into your notes? If we have log base 3 of 3, that's just going to be equal to 1. And again, the reason why is because there's an exponent of 1 on that 3 right there. We just don't always see it. Example 8, we're going to evaluate log base 7 of 49. So with what we just learned, if I could rewrite that 49 as a base 7, so 7 to an exponent, then I could cancel out my log base 7 and my base 7, and my answer would just be my exponent. Well, lucky us, we can rewrite 49 as 7 squared. So the log base 7 and the base 7 cancel out, and my final answer is 2. Example 8, part B. Same idea here. If I could rewrite 1/25 as 5 to an exponent, then I could cancel out my log base 5 and my base 5. Remember, anytime we're going from example a base of 5 to a fraction like 1/25, we're going to have a negative exponent. So in this case, I'm going to rewrite 1/25 as 5 to the negative 2. So my final answer is just negative 2.